So our next speaker is Professor Tanya Zelevinsky, and she joins us from the United States. Welcome, Professor Zelevinsky. Professor Tanya graduated from MIT in physics and math and received her physics PhD at Harvard University, where her thesis work involved precision spectroscopy of helium atoms. She joined the faculty of Columbia University in 2008 after a few years of learning about optical lattice atomic clocks at GLA, Colorado. Her research interests involve precision measurements and quantum optics, particularly state-of-the-art optical spectroscopy with diatomic molecules. Today, she'll tell us about her research work on ultra-cold molecule clocks. May I now request Professor Zelevinsky to deliver a talk. Professor Zelevinsky, would you want to take questions during your talk or at the end of your talk?
Yes, please free to just interrupt.
Okay.
Anytime.
So to enable discussions, it'll be nice if you could finish, let's say, 7 to 8 minutes before your time. Is that okay?
Yes.
Yeah. Thank you, and please go ahead. Yeah.
Thank you so much. Thank you for the introduction and for, of course, inviting me to be a part of this event. It's my pleasure to talk to you today about our work at Columbia on ultra-cold molecular clocks. As you know, quantum science with molecules has become a very exciting field recently, and it helps us go beyond what we can do with cold atoms in learning about basic chemical processes, also designing quantum materials and quantum information and computation processes, and even enhancing our work in the most fundamental aspects of physics. And these subfields are not completely disjointed. They share a lot of common challenges. For example, in order to create good qubits and to build very good clocks, one needs to ensure very long quantum coherence times between quantum state superpositions. So a lot of these subfields, a lot of this work with cold molecules really share common challenges. And this concept of long coherence times is definitely a theme in the work that I'll tell you about today. So here are a few of the questions that we address through the research that I'll talk about. We would like to understand if small molecules can contribute to our understanding of fundamental forces. And this includes both new, so far undiscovered physics, as well as old physics, such as QED, which plays a critical role in high precision measurements and also in our understanding of atomic and molecular structure. We're also exploring whether it's possible to control molecular states across a large range of the electromagnetic spectrum and how to decouple their internal dynamics from the environment for the most precise quantum control. Finally, we're also investigating whether there is a metrological advantage for using molecular versus atomic systems. The first task in working with ultra-cold molecules is, of course, creating them. Two different pathways can be used to create samples of molecules at microkelvin temperatures. One method is to directly cool molecules with an alkaline earth metal optical cycling center. So these are metals from group 2. This metal is typically bound to a halogen, such as fluorine, or to hydrogen. And it's even possible to substitute the halogen or hydrogen with a larger functional group, which can give access to polyatomic molecules. And the second method is to laser cool atoms, usually alkali metals in group 1. And these ultra cold atoms are then assembled into diatomic molecules in their ground state using magnetic or optical fields. But alkaline earth metals in group 2 have many features that are very attractive for both laser cooling and metrology. And these features also transfer onto bound molecules that are composed of these atoms. But on the other hand, these atoms don't have unpaired electron spins and are difficult to control with magnetic fields. So we have solved this difficulty by using all optical methods to create ensembles of diatomic strontium molecules in their ground state. So these are unique ultracold molecules with purely van der Waals interatomic potentials. So these ultra-cold van der Waals dimers, strontium-2, have two key features to keep in mind. But first, I'll briefly refer to the molecular potentials here on the left. There's the ground state potential, X singlet sigma G, and the lowest lying pair of potentials with the threshold at the intercombination line of strontium. So this intercombination line corresponds to the singlet S to triplet P1 atomic transition. And the pair of the potentials is called 0U and 1U. So one important property of the molecules is the presence of very narrow optical transitions that are of this singlet triplet type. And this provides a powerful capability for quantum state control. Also not shown here is another series of optical transitions. I'll mention them later, G to G transitions that are super narrow because they're forbidden by the molecular inversion symmetry. And the second important property that I'd like to point out is the completely spinless molecular ground state for bosonic strontium isotopes. And the relative simplicity of this potential is certainly an advantage for precise metrology and ab initio calculations. So to illustrate the point about the ground state van der Waals potential, here you see the ab initio calculated potential shown with red points and the experimental potential derived from traditional spectroscopy shown with the blue line. And there is a very good agreement at the level of 1%. So as I mentioned earlier, one way to create ultra-cold molecules is to assemble them from atoms that are laser cooled to microkelvin temperatures and assemble them using light or magnetic field. So our strontium dimers are created by optically making excited dimers, which then spontaneously decay to the electronic ground state of the molecule. And since the photons take away the binding energy, the resulting molecules are still at a few microkelvin. And since strontium atoms are non-magnetic, we use only optical techniques to create the molecules. The molecules are trapped in a one-dimensional optical lattice, which is just a standing wave of retroreflected light. Initially, the lattice holds the atoms in the bright microtraps, or lattice pancakes, as we call them. And then the molecules are also created in this lattice, preserving the original microkelvin temperature. And any probing light propagates along the lattice axis to strongly suppress any Doppler dephasing. This is the setup we use to create the strontium molecules by laser cooling an atomic beam that you can see near the top, and then trapping the atoms in an optical lattice and photoassociating them. This picture is actually a bit outdated, but now about a dozen laser systems are used for creating, trapping, and probing the molecules. I mentioned that the strontium molecules give us access to very useful narrow optical transitions. So I'd like to expand a bit on what we have gained from these forbidden transitions, especially the insight into basic molecular physics. Here is a schematic of an optical transition from a rotation-free level in the ground electronic state to a singly excited level near the intercombination threshold. This upper level has a Zeeman splitting in weak magnetic fields of a few Gauss, kind of a typical atomic level size Zeeman splitting. And from the linear Zeeman shifts, we could very precisely determine the mixing coefficient between the two potentials, the 0U and the 1U, that converge at the intercombination threshold. And here you see a typical Zeeman spectrum. And you also notice that it's extremely asymmetric. It turns out that this is the case because of the huge quadratic Zeeman shifts. And these exceed the quadratic Zeeman shifts in strontium atoms by a factor of 1 million. And you can clearly see the curvature even at a couple of Gauss on this plot on the right. We found that this behavior was strongly linked to the long-range dipole-dipole interaction. And this unusual behavior of the Zeeman shifts sometimes was a stronger test of the molecular model than spectroscopy alone. And I think it also nicely shows a striking difference between a weakly bound dimer and just a pair of atoms. This intercombination transition has also proven to be an incredibly useful tool in imaging the molecules and studying quantum state resolved photochemistry. In this case, the optical transition is from a ground state bound level to the singly excited continuum, and potentially back down to the ground state continuum, where the molecule is split into its fragments. On the bottom left, here is a photodissociation spectrum, which is very narrow because of the long-lived excited continuum. And the images show the side view of the emerging molecular fragments. But when we image these exploding molecules by looking into the symmetry axis of the trap, we observe non-classical angular distributions that show matter wave interference, as you can see on these calculated and experimental images on the bottom. This type of interference is really a key feature of ultracold reactions. The quantum state of the fragmented molecule is entirely determined by the well-known initial quantum state of the molecule and the photons. And by selecting their quantum states, we can control the shapes of the resulting partial waves. And we have also used this technique to probe the continuum with a high sensitivity to features like reaction barriers and collisional resonances. Here are a couple of specific examples of quantum interference effects in ultracold photochemistry. The strontium molecules are dissociated into the ground state continuum, such that all the outgoing quantum states are known, as well as their relative phase. So in both these cases, we are essentially imaging different coherent superpositions of G-wave spherical harmonics, which result in 8-fold fragment patterns. So in both cases, the experimental images are shown on the top right of each square, with the calculated predictions illustrated in 3 different ways. This long-lived intercombination threshold also gives rise to a completely new type of super narrow optical transition in the molecules, which is absent in atoms. This is a transition to the state with the same inversion symmetry as the ground state, which is even or gerade. The transition mechanism is magnetic dipole, and the strength of this effect is proportional to the bond length of the molecule squared. And this results in 2 families of excited molecular states, super radiant, which are still quite long-lived, about 10 microseconds, but their decay is electric dipole allowed, and subradiant with lifetime of order 10 milliseconds. These subradiant states provide a really nice handle for optical control of the molecular quantum states. So here we have a coherent optical Rabi oscillation on the left, and on the right is a measured lifetime approaching 10 milliseconds for a subradiant state. And these subradiant and other long-lived excited states in molecules also provide very interesting opportunities for metrology that we would like to explore. The subradiant states are extremely useful for working with molecules that are trapped in an optical lattice. We can take broad spectra of these states and see the expected red and blue lattice trap axial sidebands. That's in addition to the narrow carrier in the middle. And these precise measurements of the axial lattice trap frequency allow us to precisely calibrate polarizability measurements for different molecular states, which is important for coming up with optimal designs for molecular clocks. Also zooming in on the carrier and measuring its asymmetric width directly gives us the temperature of the molecules. Jumping ahead for just a moment, we can also see lattice sidebands with 2-photon Raman transitions between levels within the electronic ground state of the molecules. In fact, we can hide the sidebands in the clock mode when we use co-propagating Raman laser beams, or we can reveal strong sidebands in the counter-propagating configuration. So we can measure the molecule temperature directly by using the sidebands, even without using narrow atomic transitions or narrow molecular transitions that are 1 photon. While on the other hand, we can suppress the sidebands and the associated line pulling that could disturb the operation of the clock. Okay, so far I described high resolution spectroscopy of the molecules that are weakly bound, which is how they are initially created from the laser cooled atoms. But to make the best use of the molecular clock, it's important to be able to create molecules in the absolute ground state. In fact, we can now create ground state strontium-2, which is the first ultra-cold molecule of this type. And to do this, we momentarily switch off the lattice, and this removes decoherence from the light shift and results in very narrow EIT signals like the one shown here. EIT here is electromagnetically induced transparency, where the pump and probe coherently connect the highest and lowest states within the ground state molecular potential. So in this free space environment, we implement a stir-up or stimulated Raman adiabatic passage. So initially, all molecules are in the most weakly bound state, which we call V-1. Then the resonant or near resonant Raman lasers are smoothly pulsed on and off to transfer the molecules to the ground state, which is V0. We cannot see the deeply bound molecules directly, so we reverse the stir-up process and recover the molecules in the weakly bound state. And from the number of the recovered molecules, we deduce the one-way transfer efficiency, which in this plot is about 75%. More recently, we have achieved over 90%. And the black line is a simulation based on the optical block equations. And here is the conceptual implementation of the molecular clock. It involves a pair of vibrational clock states that each see the same trap depth in a so-called magic optical lattice, and these are coherently coupled to each other. So since direct vibrational transitions are strongly forbidden, we drive a 2-photon or Raman clock transition off resonantly coupling to a long-lived excited molecular state. Here, this calculation shows the intrinsic lifetimes of various clock states as a function of their binding energy in the ground state, molecular potential. So the contributions include natural decay channels and also black body excitation at room temperature. And the net lifetimes shown with the gray points in the lowest trace generally exceed 10 to the 5 years. So the clock state coherence will be set by technical limitations. So here, the details of the ground and excited molecular potentials are shown in more detail. So the absolute ground state is bound by approximately 1,000 wave numbers, and both probe lasers in the Raman configuration and the optical lattice light are phase locked to an optical frequency comb. The clock states 1 and 2 are vibrational levels in the ground state. So here 1 is the most weakly bound, while 2 is deeply bound. The clock states are coupled by a coherent Raman transition. The Raman transition is via an off-resonant intermediate excited state. And the optical lattice frequency, shown with the dashed yellow line, is red detuned from that intercombination threshold. So now let's focus on the relevant quantum states. In orange and blue are the upper and lower clock states, which have vibrational numbers 62 and 6 in this example, and no rotational angular momentum J. Moreover, the lattice is near resonance with a transition from state 2 to a deeply bound, long-lived rho vibrational state in 1U. So this state is highlighted in green. When the molecules are in an infrared lattice, the clock states are both downshifted in energy, and the molecules are optically trapped. But generally, though, the clock states will see different trap depths, and the clock transition is light shifted and broadened due to
Professor Zelevinsky, there's a question. Would you like to take it now?
Oh yeah, I'll take the question.
Yeah. I'm just seeing it about 7 minutes later. Yeah, the question is from Saikat Ghosh, and he asks why the subradiant states decay. Is there any dependence of the subradiant states with total number n, or is it just single particle effect?
Yes, this is two body subradiants. So just subradiants between the two atoms that make up a molecule. So two body, but a single molecule effect. It's not a many body effect in this case, but it is still subradiants because the physics is similar. It's sort of a suppression or a destructive interference of spontaneous decay between the two atoms, each of which could be the excited one. Because of this suppression, there is the electric dipole decay is completely suppressed. But in a molecule, you develop a new mechanism that can occur because of the finite bond length. And so you can get a weak magnetic dipole transition, and that's why they can decay. So that's the fundamental reason they can decay. And also we found that there's even a faster decay process, which is non-radiative or pre-dissociation. Still very weak, but a little bit stronger than the magnetic dipole. But the electric dipole should be perfectly suppressed.
Okay, thank you. Thanks.
Mm-hmm. Sure. Great. Yeah. So so about the clock states. So they're both downshifted in an infrared lattice, but generally the two clock states will see different trap depths. And also the clock transition is both light shifted and broadened because of the thermal spread of the molecules, and the two quantum states see slightly different traps. But when the lattice frequency is deliberately blue detuned from the green intermediate state, then the AC Stark shift pulls the blue and green states slightly closer together. And at a specific lattice frequency, this trap depth U for clock state 2 exactly matches the trap depth for clock state 1. And this is the magic wavelength at which the clock resonance then sharply narrows, since it's no longer limited by the inhomogeneous dark broadening. One way to search for a magic wavelength is to measure the clock shift versus the trapping light power at various wavelengths shown here in different colors. And the wavelength with zero slope is magic, which is the red line here. Okay, so as we sweep the lattice frequency through that narrow 1U resonance, we can directly measure the AC stark shift of the deeply bound clock state 2. So here we change the lattice frequency from 5 gigahertz below to 5 gigahertz above the resonance and see the dispersive stark shift curve. The green bar shows the lattice detuning where the polarizabilities of the two clock states are equal, which corresponds to the magic frequency. And here is where we expect to see the narrowest clock resonance or the longest coherence time of the clock state superposition. And here we directly plot the clock resonance line width. As you see, the baseline shows a nearly 100 kilohertz width due to lattice-induced broadening, and the line width increases further as we approach the resonance. But at the magic frequency value on the blue side of the resonance, it drops dramatically by over 3 orders of magnitude. So here are a couple of clock spectra on either side of the resonance, but both away from the magic frequency. And we see the expected light shifts and broadening from the lattice light that are both of the order of 100 kilohertz. But at the magic frequency, the resonance is symmetric and very narrow. So this is the zoomed in spectrum of the vibrational clock resonance at a magic lattice frequency. This resonance is 30 hertz wide, which is a 3,000-fold improvement over a non-magic lattice wavelength. The resonance frequency for this clock state pair is 25 terahertz. So this spectrum corresponds to the quality factor of 8 times 10 to the 11. Besides using the narrow width of the clock resonance to quantify the coherence of the clock states in the magic lattice, we can directly drive quantum Rabi oscillations between the clock states. So essentially, the molecule is made to oscillate between its tightly bound state and its weakly bound state with a long bond length. And a well-chosen magic frequency helps us reach very long coherence times for the molecular clock. So here's a Rabi oscillation between the molecules in vibrational states that are separated by nearly 30 terahertz. The oscillation decays with a long time constant of 130 milliseconds. So we're not yet limited by the two-body collisional lifetime of the molecules that's shown here with purple triangles for the upper clock state. But instead, we are currently limited by the lattice-induced loss of molecules in the lower clock state, shown here with the red squares. And here's some more. Yes.
Sorry. Would you like to take one more question?
Yes.
Yeah. This is being asked by Professor Saikat Ghosh. He asks, why is it magic? Is there cancellation of light shifts for so many levels too?
Yes. So back for a moment to here. It's magic for the two clock states 1 and 2, because the lattice that connects state 2 to this excited state shown in green, it pulls the blue state up because of the stark shift between the blue and green states, and then it matches the frequency of the clock states. So the trap depths of the two clock states marked as U are exactly the same. And that happens at a specific frequency, sort of on the blue tail of the lattice-driven resonance, which is a couple of gigahertz to the blue of the resonance. And so so that's exactly when the line width narrows in the middle plot. And here is where we see this narrow resonance. And also here is where we take the Rabi oscillations for the longest coherence times.
Thanks.
yeah, so we are very happy with this 100 millisecond coherence of states that are separated by tens of terahertz. But still, we are interested to extend them even longer for even a better clock. So we take a more careful look at the lifetime of the deeply bound clock state 2, which is the one that limits the coherence time of the fringes. So if we put the lattice frequency away from this magic value, meaning quite far from any lattice-driven resonance, then the decay of that state just shows a typical two-body decay with more than half of the molecules are still remaining here after 100 milliseconds. So this is the green trace. And the magnitude of the two-body loss coefficient beta is quite typical for ultra-cold molecule systems. But at the magic wavelength, shown with the magenta trace, the loss is much more severe with almost no molecules remaining by 100 milliseconds in this case. And this magic lattice loss is exponential rather than two-body, potentially indicating lattice light scattering. But from our knowledge of the lattice-driven transition, we were not expecting such fast loss. And this rapid loss can be studied as a function of lattice light intensity, as shown in this inset. So you can see that the loss rate, or the scattering rate, does increase with the lattice intensity, which is the x-axis. So the lattice light is a limiting factor. However, the scattering seems to increase quadratically with the lattice power, which is the red line parabolic fit. And this may point to two-photon lattice-induced photodissociation. So with our theory colleagues, we have looked into this process and found that it should most likely be weaker than what we observe here. So this rapid lattice-induced loss is not entirely understood. However, we do have a way to design the clock to minimize this loss by choosing an optimal 1U state for the lattice-driven transition. In other words, we look for a magic frequency where the lattice is more detuned from a resonance. And in practice, it should be detuned by more than 1 gigahertz, which can help with a number of technical issues. So how do we choose the best magic wavelength? So this plot uses colors to show the coupling strengths, or transition dipole moments squared, DMS, between the ground state vibrational levels, which are all potential clock states on the vertical axis, and 1U excited states on the horizontal. The brighter colors indicate stronger coupling, and we see a typical pattern with kind of two main branches, which arises because the molecule spends the most time at its inner and outer classical turning points. And since we're interested in at least one deeply bound clock state, here I zoom in on the lower left corner that shows coupling strengths for the lowest 10 vibrational states. So near the bottom of the potential, the energy structure is fairly harmonic. And this shows up in this checkerboard pattern of low and high transition strengths. So our first experiment used the state pair highlighted with the white square. And it's relatively strong, but it doesn't sit on one of the branches. And for the next iteration, where we obtained the Rabi oscillation that I showed today, we chose the black square for the magic lattice, and the oscillations lasted 4 times longer. And I would like also to highlight that identifying this checkerboard pattern of lattice-driven transition strengths really helped us with the spectroscopy of the excited state and with assigning quantum numbers to the spectra. So there are over 120 states in the excited 1U potential, which means that despite the 1% precision of the ab initio calculations, we still can't be sure of the state's vibrational quantum number only from its binding energy measurement. But this distinctive pattern helps us identify the correct vibrational quantum number for the excited state. And here I show calculations corresponding to row number 6. and also precise measurements of the selected transition strength. So we find that there is a unique way to combine energy level spectroscopy with transition strength to get the correct quantum state numbering. And the magic lattice detunings that are measured and shown in the bottom plot. And the largest detuning with the arrow has produced the longest Rabi oscillations. And very recently, we found a magic wavelength with a detuning.
Excuse me, here is another question.
Yes.
It's asked by Bimalendu Dev. So is it possible to find a magic wavelength to trap both the molecular state and free atom dissociated state?
Well, usually a magic wavelength is, a lattice can be magic for a particular pair of clock states. It's very unlikely that you can find something that's magic for more than two, like 3 states. Usually we don't find it's necessary because there's one clock transition that you want to really enhance the precision of. And the rest, you just need to be able to do some manipulation. So you want to choose something without too much broadening, but true magic wavelength is usually necessary just for a pair of states. Of course, in this case, in the case of molecular clock, there are many potential clock transitions, and it would be great to have a magic wavelength for more than just one pair. But that's not usually easily possible, unfortunately. But we're still thinking about what is the most practical way to kind of approach that.
Thanks.
Yeah, sure. Great. Yeah. So again, this black rectangle gave us a better result because it's a stronger lattice-driven transition with a larger detuning. And much more recently, we found a magic wavelength with a detuning of nearly 5 gigahertz, which is larger by yet another factor of 2. And in fact, the largest we expect for this molecule. And its transition strength is highlighted here with a red rectangle. It's the brightest one that we can choose. And here we have experimentally found the polarizability resonance with this nearly 5 gigahertz magic detuning. And this magic lattice, which happens to be at 1005 nanometers, we can expect to achieve even longer clock state coherence times. So I'll skip this part. And I'll say here that even our current implementation of the molecular clock is already precise enough to start providing useful results for the dimers of the dominant strontium-88 isotope. So here is a fairly coarse preliminary scan of the bottom of the ground state van der Waals potential, showing the 7 lowest vibrational states. And we also have precise data on the top of the potential corresponding to vibrational numbers above 60. And this data was collected using a 2-photon Adler-Towns spectroscopy, as you can see in the sample scan, where even the initial precision for some of the selected states is already more than 4 orders of magnitude higher than in previous work. A bit more generally, a molecular clock that provides these very precise measurements of the vibrational states is an excellent sensor of the interatomic force. So when the positions of the bound states are known with an uncertainty below, say, a part per trillion, then the interatomic potential and the binding force that holds the molecule together can be reconstructed with a similar precision. And this is, of course, in addition to other exciting applications of molecular clocks, such as metrology in the terahertz regime and measurement of the temporal stability of the electron to proton mass ratio. But regarding the force sensing, this high precision interatomic force sensing can even lead to discoveries of new physical forces. So for example, it may be possible to use the molecular clocks to learn about gravity in the ultra short range. So our strontium molecules can be pictured as pairs of atoms separated by their bond length, which can vary from about 0.5 to 5 nanometers. And this bond length is set mostly by electromagnetic interactions, of course, between all the electrons and nuclei. But since the nuclei are relatively heavy, Newtonian gravity also contributes and makes a very tiny correction to the bond. And possible deviations from the Newtonian gravity can be parametrized, for example, using the exponential Yukawa term with a magnitude A and length scale lambda. From previous experiments that use quasi-classical methods, we know that at the nanometer scale, A is smaller than 10 to the power of 22. So in other words, there could be a huge correction to regular gravity, and it wouldn't contradict any experiments that have looked at interactions between spinless masses. Whereas our molecular clock is a fully quantum system that has the potential to go to higher sensitivities. And from the theory point of view, the possible fifth force would be a small correction to the electromagnetic forces. And in the basic Born-Oppenheimer picture, the energy of a bound molecule consists of the electronic, vibrational, and rotational contributions, although our molecules have no rotational energy. And the strontium-2 ground state potential supports 63 bound states. And the energy corrections beyond the Born-Oppenheimer include adiabatic terms that are proportional to mu, the electron to nucleus mass ratio, and non-adiabatic or mu squared corrections, various relativistic and QED corrections that can depend on both mu and the fine structure constant, and finite nuclear size corrections that implicitly depend on the nuclear mass. And the theory is still under development, but we believe it should be possible to describe the leading order corrections analytically with coefficients that could be partially fitted to the data, isolating mass dependencies that could signal a gravity-like force. So specifically, strontium has 3 spinless isotopes that can form
Professor
dimers.
Zelevinsky, sorry.
Yeah.
If you can, in 2 minutes, if you can finish, then we can take some questions. Is that okay?
Yes, I will conclude shortly. Yeah, so just one of the last things I want to mention is that strontium happens to have 3 spinless isotopes that can form dimers of multiple mass combinations, supporting a total of hundreds of clock transitions. And these could provide plenty of information on mass dependence across all bond lengths. And also various corrections shown here have different asymptotic behavior with bond length, which can help distinguish, for example, QED effects from new physics. Okay, so to summarize, we have created ultra-cold van der Waals molecules in the absolute ground state. We use these molecules to demonstrate a vibrational molecular lattice clock, which now achieves a quality factor of approximately 10 to the 12. And coherence time of 100 milliseconds across the molecular potential depth, with still a lot of potential for improvement. This clock was first proposed some years ago for measurements of slow time variations of the electron to proton mass ratio, or mu dot. But we're also excited about its applications to sub-part trillion interatomic force measurements and the potential search for new mass-dependent forces. And finally, I would like to thank my graduate students, my research group who worked very hard on these experiments, particularly here, Con and Emily contributed significantly to the strontium work. And also we are very grateful to our theory colleagues, Robert and Ivana from the University of Warsaw, who are working very hard on the ab initio high precision molecular calculations. And thank you very much for your attention.
Thank you. Thank you. So now the floor is open to questions. We'll start with Sourav. Sourav, you can unmute and ask.
Oh, hi. So very nice talk. So I was just wondering, to ultimately want the theory to be at the same level as experiment. So at present, how do your experimentally measured binding energies compare with the theory calculated or the vibrational energy? I mean, at what level?
That's right. Yeah. So the theory is still under development. So it's hard for me to say exactly what the precision will be, but I can say for sure that it's not going to be as high as that of the experiment, because if we already have, you know, easily the 30 hertz line widths, which we can average down to well below a hertz, and that's for the largest frequency. Certainly, we can do even better for smaller frequency splittings. And there is no chance right now to have ab initio theory to get to a hertz in a big molecule like strontium-2, even though chemically it's a very simple molecule. So for that reason, here I'm, you know, we're thinking about doing a combination of, firstly, thinking about doing isotope shift. Because ab initio, there are lots of non-mass dependent contributions that will be fairly common to the different isotopes. So we'll try to take them out by looking at different isotopic masses and just doing it as a function of mass. So that would be a great simplification. And another thing is that for each mass combination, we have these 60 transitions where all these beyond Born-Oppenheimer terms have a different behavior with the bond length. So as you scan through all the transitions, you get to different bond length, and you can isolate them this way. So it'll have to be a combination of ab initio theory and a lot of data, not only ab initio, because that's too difficult.
So just maybe related question. So you said van der Waals. So at least theoretically, I mean, is the C6 that you measure, C6 coefficient, does it match with the theory? So I would presume that strontium atomic calculations are quite good, much better than the molecule. So is there a way to at least say that the C6 measured in the experiment will match the theory very well, or no?
You know, that's a good question. I don't have the numbers specifically on C6, but you know, here I showed just the just a second here. I showed the ground states very roughly. It's a very small picture, but it's a calculation here in the bottom right. The ground states ab initio. This is not really fitted, and then experimental, not from our experiment, but from more traditional sort of less precise spectroscopy. And for ab initio, you know, 1% or below 1%, that's a very good agreement. But of course, that's very far from what we need. So we're going to these well beyond Born-Oppenheimer terms. But for us, you know, we worry not just about this tail, right, the long range tail, but actually about the entire potential.
Yeah. Okay. Thank you very much. Yeah.
Sure.
Professor Bimalendu, can you unmute and ask the question?
Okay. So the upper clock state seems to be excited vibrationally, and it is in the high vibrational level. So is the vibrational relaxation not a problem in this context?
Right, is what not a problem?
Vibrational relaxation.
Oh, yes. So we can, this is the calculation here of the lifetimes that include black body excitation and natural relaxation. And if you, the net, so these are different contributions, but the net lifetimes are in the bottom trace in gray, and they're all measured in multiple years. So it's very, very slow.
Any further questions? If not, let's thank the speaker. And thank you so much.
Yeah. My pleasure.